Testing and debugging embedded systems often involves looking for clues that can be hard to discover if you're only looking at a single domain. While correlating signals across multiple domains has traditionally been a painful and technically challenging process, SpectrumView on our 5 Series B MSO offers an incredible solution. SpectrumView uses patented hardware built into the analog-to-digital converter, which we call the Tech49 ASIC. Inside the Tech49 ASICs are digital down converters, which optimize analysis based on the selected center frequency and span settings. This analysis is a more computationally efficient way to display the spectral content of the signal, enabling best-in-class analysis and measurement results. This technology gives you the ability to independently control the acquisition settings for the time domain and for the frequency domain. And when we only want to acquire a few cycles of this clock, the traditional FFT in our top left corner doesn't have enough samples to provide meaningful data. And when we need to acquire a longer record, the FFT doesn't have enough sample rate to resolve these frequencies. Notice that throughout all setting changes, the SpectrumView display in the top right remain unchanged. It was not affected by our changes in the time domain settings. When required by my analysis, I have complete control over my center frequency, span, and resolution bandwidth. SpectrumView also enables us to look at the variation in RF magnitude, RF frequency, and RF phase as it relates to our acquisition timescale. In this example, let's turn on frequency versus time. It looks like this frequency is modulated in a triangular pattern. I can quickly change our hardware edge trigger to the frequency versus time waveform and stabilize this triangular wave. Adding a few measurements, we can determine the frequency deviation and period of the triangular modulation. It looks like the spread spectrum clock varies 3 MHz from our 98.5 MHz center frequency, with a period of 25.5 microseconds. Another capability is that each of these 8 inputs can be individually configured to view a different center frequency. Let's connect channel 2 to a 40 MHz clock to see this in action. Notice that channel 1 SpectrumView is centered on 98.5 MHz, and channel 2 SpectrumView is centered on 40 MHz. No matter how many channels we add, each can be configured to its own center frequency. We can overlay the SpectrumView windows to get an easier visual comparison to see interactions between signals. I'm not sure if you noticed, but every once in a while, the channel 2 SpectrumView signal seems to jump. Let's turn on the frequency versus time trace for channel 2 and configure a frequency versus time trigger on the channel 2 signal and lengthen our acquisition. Let's take a single acquisition. Okay, this rectangle is called spectrum time, and it allows me to select exactly which portion of our acquisition is represented in the SpectrumView window. See, as I drag spectrum time around, the SpectrumView window is updated with the RF content derived from this exact time window in our analog acquisition. This lends itself to an incredibly diverse set of use cases, including EMC troubleshooting. You can even connect a near-field probe to one of these inputs and correlate power supply sequencing, serial communications, or active component behavior with your electromagnetic emissions. And when you're interested in more advanced RF measurements, you can install SignalView PC on your instrument, which will enable immediate vector signal analysis for measurements such as modulation analysis, adjacent channel power, spectrogram display, pulse analysis, and more.